So today we will go over the overview of this course that we didn't have enough time to do that last time. And some of you asked about what are the possible projects that we can do. So I'm going to introduce some sample project, and then we'll talk about propositional logic. Okay. So this was the course structure. So classical logic is not the main thing that we are going to look at here, but this is so much of foundation for many of the KR formalisms. So we will study this. For those of you who took a logic course before, or some intro to AI course, this might be some overlap, but in any case, we want to make it more formal so that we can build our theories on this classical logic. So it is a good idea to review the materials, or if you haven't encountered this material before, then it's a good idea to learn now. Okay. So we are going to, after that, actually, we are going to go into logic programming, in particular known as answer set programming. And then we'll talk about ontology, okay? And then we'll go into the probabilistic foundation. And after that, we will talk about the combining the logical foundation and probabilistic foundation. And also we'll talk about another integration of logic and probability that is derived from Markov logic and answer set program. And if time permit, we'll talk about actually not the neural network per se, but how the neural network can be integrated with knowledge representation, which is actually more up to date. If it was maybe last year, it was not possible to introduce this topic, but just in recent months, there are a lot of interesting ideas coming in here. So I hope I can introduce some of the interesting ideas, and some of you may want to do some project on that too. Okay, so here the blue parts are what we will focus, and the green parts, roughly we are going through that, but we don't probably have enough time to cover in very detail. But if you want to study in more in depth, I can give you more reference, and you can do project on those topics. Okay, so what is classical logic? So classical logic is actually the foundation, as I said, and logic is known as calculus of computer science. And there are actually a lot of logic that has been invented by mathematicians, philosophers, and even computer scientists. We will not go over many of them. We will focus on the very basic classical logic known as propositional logic and first-order logic. Okay. There are other logics like second-order logic. Sometimes people do third-order logic and model logic. They are all interesting ideas, and some of the KR area heavily rely on those things. In particular, like the multi-children puzzle that you saw last time can be formalized in model logic. Okay, but we'll not go over that in this course. Again, if you're interested, you can explore that area as your project. So the main idea of classical logic was to study the mathematics. So when people write a proof, what is actually a valid argument? Why some people say from this and this argument follows? How do we know that this is a sound reasoning? This is what logicians and mathematicians were interested in. So it was not invented for AI, but AI embraced logic from the very beginning because it is the kind of reasoning that people also make. Very typical example known for many, many years is modus ponens, right? So man is mortal, Socrates is man. What do you include? What do you conclude from there? Okay, Socrates is mortal, right? So that is actually known from the ancient Greeks, and this is so much fundamental to human reasoning too. But we also talk about a few other examples last time that this kind of mathematical logic cannot be used for formalizing some human level reasoning. Okay, so like the non-monotonic reasoning or default reasoning that we talked about, they cannot, some of the problems that are very easy for humans are not easy to do in logic. Okay. All right, the next part is, so in order to overcome these kind of difficulties, there are some proposals. One of them is knowledge-based declarative programming method. Here we will talk about answer set programming, which is roughly, I don't know, there is some similarity between this one and the prologue, but that is only in the syntax level. The semantic level is actually very, very different. This is a declarative logic programming paradigm that is suitable for knowledge-intensive and combinatorial research problems. One thing that you will probably have some challenge in here is you need to learn the new model semantics called stable model semantics, which is not the easy thing to learn if you're learning for the first time. So that's why I want to spend some time on classical logic, so that when you migrate from the classical logic to the stable model semantics, maybe that's easier to do. Okay. Now the problem with classical logic is it cannot express many useful ideas in human reasoning, like defaults, recursive definitions, aggregates, and preference. So we prefer this over that, but in classical logic, every model is kind of similar. Okay, you cannot really distinguish between which one is better. Okay, so this kind of thing can be overcome by tweaking the classical logic semantics, and that is known as stable model semantics. Okay, so origin is classical logic, but you have to know how this can be tweaked. Here, the idea that you are going to explore is you want to solve some problem, and basically you need to know how to represent problem in some formalism, and then use the tool called answer set solver to find the solutions. And if you find the solution from the answer set solver, this will be exactly the solution that you are looking for from the original problem. Okay? So here is a diagram to explain this idea. So when you want to solve the problem, okay, this is similar to the picture that you saw in the first class when we modeled the world in terms of symbols and manipulating the symbols to derive the new information, right? So same way, if you want to solve the problem, there is actually the problem that you are given. Now you have to feed this problem into computer, okay? And the computer outputs, and that's the solution that you get. Okay, so that's how you do. Now, in traditional or procedural programming that you are familiar with, this part, turning the problem into program, is called programming. So you know how to do the program, right? How to write a program to encode the problem into some executable form. Now, of course, program to generate output is called execution. So you execute the program to generate output. Now, this output you interpret to be the solutions. So to solve this problem using computer, we go this way. Okay? Good. Now, what is the difference in the declarative programming, like what answer set programming is doing? Here, it's similar, but problem will be modeled, okay? And that will be the representation. So we are going to represent the problem. Here, the difference is we are not necessarily giving the algorithm to solve the problem. We just describe the problem. Okay? So we represent problem into the format that computers can understand. But once we do that, the nice thing is, even though you didn't give the algorithm to solve, there's a general purpose algorithm behind this solver that's find the solutions. So it produces the output, and from the output, you interpret the solutions. Okay? So this is something that you are going to learn first after classical logic. Without giving the algorithm, how can I solve this problem? Okay? So if you can represent this problem in a correct manner that computers can understand, then you're done with that job. The rest is done by the computer. Okay? Of course, you have to, here in class, we will see how that can be done in general. Okay? Reasoning about actions is kind of put together with answer set programming section. Although it does not have to be, there is actually a separate maybe class that can be taught about reasoning about actions. Here we will use answer set programming to model the reasoning about actions. So here is one of the typical application of answer set programming to model the dynamic world. So if you want to model some changes in the system. So some robot performed the action, it changes to another state, and from this state, some other actions can happen, and it goes to another state. And then you want to see what are the sequence of actions that I can execute to reach to the goal. Okay, that's called planning. And planning is one problem in the area of reasoning about actions. You can also talk about what will happen if I do these actions, what will be the result. Okay, if I eat this and don't do exercise, will I be in trouble? Okay, you can do this kind of temporal projection problems. Okay, so we'll learn those kind of aspects. Here, the idea is to develop the systems of formalism for describing actions and their effects. And we will talk about action languages, which is built on ASP, programming, but is more high level, and it gives us concise and convenient ways to describe a transient system. Okay, so we'll talk about transient system later in more detail. The next thing is ontology. So this is a bit different area. So when I show you this picture, the areas are not actually subsuming each other. So here, this is a kind of different part of knowledge representation where people are interested in ontology. So ontology is a very philosophical term, but in computer science, it's basically conceptualization of object. So we talk about this object belongs to this class, or is a member of this class, and if the class has this property, then its subclass also inherits the same property, so things like that. And there has been a lot of work on developing very large ontologies, and it captures actually various areas of human knowledge, and it is actually being used in applications. Okay, so there has been developed many. There has been many languages developed for this, but in recent years, the building upon the old ideas, there came out more practical language where people actually agree on the standard. So that actually boosts up those building ontology effort. Okay, so you may have seen some systems like IBM Watson system that actually beats Human Champion in the Jeopardy quiz show. Where does Watson get the knowledge? It's actually from some big corpus of knowledge, could be DBpedia or Wikipedia or whatever the unstructured and structured knowledge base. The idea here was close to the semantic web effort. Watson itself didn't use the semantic web language. They used their proprietary format, but later when people try to duplicate effort of Watson, they use actually the standard RDF or semantic web languages. Okay. So this is actually not the traditional semantic web layer cake. This is a kind of updated ones. So we are not going to touch on everything about semantic web. This is not a semantic web course, but we will talk about RDF, which is the data interchange model in the semantic web, and SPARQL, which is a query language, a bit of RDFS, and OWL. Okay, so this will be mentioned in this class. So in case you haven't seen what is RDF, it's basically the graphical knowledge base, and the node represents the instance roughly, okay, the objects, and the edge represents the relation between the object. So here you can say Anne Hathaway married to Shakespeare, who lived in Stratford, which is in England and which is part of UK. Okay, so this knowledge can be encoded in the graphical structure. Okay, and you can see that Shakespeare. So Shakespeare wrote King Lear. He wrote also Macbeth, whose setting is in Scotland, and Scotland is also in part of UK. So RDF triple is basically this edge. So this object, and also it's called predicate, or also it's predicate. So subject, predicate, and object. Okay. And SPARQL is a query language for RDF. In case you are familiar with SQL, it's pretty similar to SQL, but there is also some differences. Okay. Yep.
Each of those nodes is considered like just a noun or an object, or is there?
It's just any object. So object can be also abstract things, okay, like love, or it can be a particular instance, okay, or it can be a class as well. So, yeah. Okay. In fact, as you see from this layer K, RDF was not supposed to be the very expressive language. It was more like the data model. But the more concept of ontology was supposed to be represented more in a higher level language like OWL and rules. The problem was these standard effort got delayed, and people somehow found out that RDF with slight update with RDFS was enough to represent lightweight ontologies. And it was successful. It has been successful for many domains. So that was, yeah, okay, kind of overused language in some sense. Okay. Now this is the DBpedia, which is written in RDF. Okay, so this is, of course, you cannot represent this graph in computer easily, right? You have to turn this into some format that computers can understand. So it's basically kind of the database table. So it's about here is the subject. So this is Angelina Jolie, and this is the property, or the predicate, okay? And this is the object. So to answer your question, these are the possible things, okay? But it could be actually more than that too, okay? So as you see that I didn't know about this, Angelina Jolie is actually younger than me, and her citizenship is in Cambodia. I didn't know about that, okay? But anyhow, so there's a lot of knowledge that you can actually see from this what question answer can be made of, okay? So we will talk about those things. Now, web ontology language is building upon the data model of RDF. It's supposed to do more expressive ontological reasoning, where RDF and RDFS basically do a bit of simple class membership. But it doesn't say about whether this class and that class are disjoint, or whether this class is a subclass of another class. There's a lot of limitation in RDF for ontological reasoning. And this is the format that is in format in OWL. Here a particular example is about how to describe meaty margherita pizza. So in English, it is any pizza that has some tomato topping and some mozzarella topping and some spicy beef topping, okay, can be represented in in this kind of weird format, okay? But you'll learn why this makes sense. And the basis of OWL is description logic, which was actually invented long time before this semantic web languages, okay? So what you will see is this is a logical notation in description logic, where you can define happy man to be a human, which is not female, and who is married to a doctor, and all his children should be either doctor or professor. Okay? I mean, you don't have to agree with this definition, but this is how one can write the definition of happy man. The second line is saying that every doctor is a human, okay, things like that. So the third one is this is class of object that is married to a human, okay? And this one says whoever has a child which is a human, who is a human, must be a human, okay? So as you see, this kind of knowledge has to be encoded in some ways so that computers can understand. And this is how it is done in the OWL language, okay? And surprisingly, this one is basically just a shorthand notation for first order logic formulas that you are going to learn soon, okay? So the reason that we don't write first order logic formula here directly is because it's too complex to look, but also it is undecidable, so we cannot use it directly. I'm going to talk more about the complexity and computability issue later, but basically the message here is this is a restricted subset of first order logic. Okay? So one reason that we are going to go over the classical logic in the beginning of this semester. All right, so after then, we'll turn our gears into probabilistic foundation. And here, if you took Intro to AI or some other courses, you may have seen BaseNet, which has been the driving force of AI in before the deep learning time. So BaseNet is basically a combination of graph theory and the probability idea. Okay, so here there is a graph that represents kind of relation between those components. So for this here, tampering causes alarm, fire causes alarm, or fire causes smoke, alarm causes leaving causes report. So there is certain relationship that is known here, and then there is also the probability table associated with each node. So to say that it's not always that alarm causes leaving, okay? With some probability that alarm may cause leaving, okay? And I said actually cause, but it's actually not the correct word to use. It's really not the causality that the BaseNet is trying to represent. So the very inventor of BaseNet, Julia Paul, turned into another formalism called causal network. Okay. But anyway, we are not going to study that here. But this is actually the kind of well-used formalism. But in this class, we are going to talk more about the Markov net because we will use this as a foundation of Markov logic that comes after. Okay. So Markov net is similar to BaseNet except that the graph are undirected. Okay, so there is no arrow direction in this graph. And also the difference is, as you see, in BaseNet, this was the probability. In the Markov net, these are just arbitrary numbers. It's not necessarily probability. Okay? All right. So after that, we will talk about Markov logic. Here, the idea is to combine the idea of first-order logic and probabilistic graphical models. And throughout the semester, you will see that each of the formalism has its own strengths and weakness. And this kind of effort has been continuous in the area. So how do we combine different formalism to overcome the deficiencies in each of them? Okay. So what is the limitation of first-order logic? It's too brittle. So we talked about the example last time that even if there is a single exception to the statement, the exception is fails, right? So even if I walk to the car, okay, normally the car does not disappear. But if there is a chance that the car can disappear, I cannot prove that the car will remain. Okay, so that I cannot prove that my plan can be successful. So even single exception can make the whole formulas to be invalid. That is actually the problem. So what Markov logic is trying to do is to overcome that. So the formulas are being weighted so that some formula with higher weight is more likely to be true, but it's okay to get the formula to be false as well. Okay? So this actually links between knowledge representation and machine learning area because the idea is where the weight comes from. Okay, how do you know that this formula is more true than the other formula? Okay, in early days in AI, people try to when people develop so-called expert system, they saw the very idea was there as well. So we want to say when you diagnose some patient, not all the patient who has some disease A shows the symptoms B, right? I mean, more likely to show symptom B, but not always. So how do we kind of weight this kind of thing? If you have more evidence of these symptoms, then you can say that the person has this disease, but not everyone is actually showing the same symptoms when they have this same disease. Okay? So what they did was to use some sort of weight to these rules. The problem was when the domain becomes very large, it's very difficult to maintain this weight. Okay, so somehow there's a new knowledge comes in, then the human has to find what was my weight to this particular rule. If I change this rule weight, then it changes all other things as well as a consequence. And it was so difficult to maintain the soundness of the sound reasoning that can be done in those systems. Okay. So the difference here is now the idea of Markov logic is getting this weight from the data. So humans don't have to worry about what weight to set. It's learned from the data, which is actually win-win situation. Okay. And here also the nice thing is the logical reasoning is very precise. The disadvantage here is the complexity is too high. Okay. So even for propositional logic, you know that satisfiability problem is NP-complete. Okay, but if you relax this to go into probabilistic inference, although your answer may not be accurate or 100% correct, but maybe 99% correct, but much, much faster. Okay, so that kind of sampling method or probabilistic reasoning has certain advantage in there. Okay, all right. So LPMLN is another language which actually derived from Markov logic and SSA programming. We're not going to spend too much time on this because if you learn already ASP and Markov logic, this will come natural. There is certain limitation of Markov logic which can be overcome by LPMLN. Okay, and I don't have slides for the neural network, but there is also some materials that we'll cover on that. Okay. Well, I can mention that in particular what is going on these days is the knowledge graph. So knowledge graph like RDF graph that you see, people try to convert that into the neural network. Okay, so in the vector space, and then do reasoning on that instead of the SPARQL like query search. Okay. All right. So that's all for the course overview. Any question up to this part? Okay. Okay. So are we ready to start the content? Let's see. We have about 30 minutes, and probably that's enough. Okay. So I know some people may be bored, but in any case, I hope we can have some uniform language so that we don't have to worry later. Propositional logic is one of the actually simplest logic, okay? And the idea was, of course, logic was there even before computer, right? What is relevant in computer science is satisfiability problem in propositional logic is the first problem known to be NP-complete. If you don't know what is NP-complete, talk to me later, or you can Google, or you can ask on the Piazza. Basically, rough idea of NP-complete problems is very difficult. If you want to solve it, you will take unless P equals NP, you will take exponential time to solve this problem in the worst case. However, that is actually not necessarily the bad news for KR. In KR, many problems are actually starting from NP. Okay, they're actually more difficult problems than NP, like sigma 2p, sigma 3p, and so on and so forth. So NP is kind of right problem for KR. Okay, and there are actually many efficient set solvers that solve the satisfiability problem in propositional logic, and it has been used in many areas in computer science. not necessarily in AI, but also in hardware verification. Okay, so they use set solvers to verify the properties of some hardware or actually software system as well. So, what is propositional logic? It has many different names, but we'll just use propositional logic. You can see that like a Boolean algebra or Boolean logic. Okay, so that's also the same thing. In propositional logic, there's something called atom. An atom is something that we assign the meaning true or false. Okay, so this is the basic unit in propositional logic. And here, one requirement for being an atom is it has to be evaluated to true or false. Okay, so for instance, the sum of the numbers 3 and 5 equals 8. Can this be an atom?
Yes.
Yes, because it can be either true or false. Is it true or false? It's supposed to be true, right? Okay. Jane reacted violently to Jack's accusations. Can it be an atom?
Yes.
Yes. Is it true or false? It depends, because we don't know who is Jane and Jack, but if there's, those people exist and if there is something about them, this is something that you can check true or false given the particular situation, right? Every even number greater than 2 is the sum of two prime numbers. Can this be an atom?
Yes.
Yes. Is it true or false? False. Okay, so what that here, let's see, is it? So every even number greater than 2 is the sum of the two prime numbers. And when you say false to the claim about every number, that means you have a counterexample, right? What is a counterexample? Somebody
Prime
said,
numbers have to be equal.
no, it doesn't have to be.
Can they be equal?
Well, it can be equal, it may not be equal. It doesn't say. So that's okay. Can be equal. What? So what even number cannot be represented by the sum of two prime numbers?
6.
6. Okay, so 6 cannot be represented as sum of two prime numbers. True or false? False. So that doesn't solve. Why? 6 is equal to 3 plus 3. And 3 are primes, right? 8? 8 is 5 plus 3. And 5 and 3 are prime. We're in trouble. But does it mean? We tried a few examples but didn't work. Does that mean that this is true? So we agree that this is true. This is an atom. It can be either true or false. Okay? We simply don't know whether this is true or false, right? But somebody else may know this answer, right? Is it? Unlike the second example, I don't know who is Jane and Jack and whether they reacted. Jane reacted violently. I don't know, but if I am given the particular thing, I can answer, right? Now, here, I know what is even number. I know what greater than means. I know what is 2. I know what is sum. I know what is prime. I don't have to refer to anything else, right? But I don't know whether this is true or false. So you're still saying this is an atom. Oh, that's every, right? But every doesn't change whether this is true or false. If there's a single exception, then this whole sentence is actually false. Okay, should I give you as a homework? This is actually known as gold box conjecture. Nobody in the world knows the answer yet. Okay, so it's fun. Okay, so this is a simple sentence. Okay, and we know what that means. So we cannot really say yes or no yet, okay? But this can be either true or false. The definition is saying it can be either true or false. It cannot be both true and false, right? So this will be assumed to be an atom, okay? Yep.
So it's kind of equivalent to blue, right? Blue and green, the hypothetical philosophical.
I don't know what this.
You know, okay.
We can talk offline. Okay. Yeah, maybe there's some connection to that. Now this red sentence, is it an atom? Could you please pass the salt? It's not. It's not something that we can assign true or false. Okay? Ready, steady, go? No, it's not. Okay? May the force be with you. This is not something that you can assign true or false. Okay? So these red sentences are not atoms. We are not going to look at these sentences in propositional logic. Only the blue part. Okay? So the sentence that we can say either true or false will be called atom. Okay? So that's half of propositional logic. The other half is once you have this atom, you can compose the meaning using some logical operators known as conjunction, disjunction, implication, and negation. Okay? So here's a formal definition. Okay? So a propositional formula comes from the signature, sigma. I didn't mention what is a sigma, but sigma is basically a set of atoms. Okay? So let me say sigma or signature is simply a set of atoms. Okay? Now, given this signature, you can build a formula in a recursive way. Every atom in the signature is a formula. If I say P, so suppose our sigma is PQR, okay? Each of the symbol P, Q, and R is an atom, okay? Now, besides these symbols, there's also called zero-place connective. I just copied from the reading material, so I didn't copy correctly. There are two designated symbols which are not in the signature, but works like an atom. And they are called bottom and top, which basically represent false and true. Okay? Okay, so that's the base case. And the recursive case is if you know something is a formula, you can prepend the negation in front of it, and that also becomes a formula. So if I know that P is a formula, I know P is a formula because the case 1 says every atom is a formula. Then now I can put negation in front of it, so it is a formula. Now once I know that not P is a formula, I can also prepend another negation, this is also a formula. And I can repeat this on and on. Okay? So that's the recursive case for the third clause. The last one is saying for binary connective. So I just denoted this not to be the binary connective, but there are conjunction, disjunction, implication, and sometimes also equivalence, and so on and so forth. Okay? So if I know that this is a formula, and I know that Q is also a formula, then I can combine it with conjunction, or disjunction, or implication. So each of these are also formulas. Okay? Now once you have that, you can also prepend another negation, or can combine with another one. Okay, so that's also a formula. Any question up to this part? Yes?
You have stated the zero-place connective.
Zero-place connective is like an atom. So far, this is just a syntax, so there is no meaning yet. Roughly corresponds to false and true. But I can just write bottom, and this is a formula. Okay? And I can put a negation in front of it. This is also a formula. Okay? The meaning will be explained in the next slide.
Why are they called zero-place connective?
Oh, it's because these are the connectives that, so, I mean, this has no argument. The bottom and top doesn't have any argument. Negation has one argument. So that's a unary connective. And the others in conjunction, disjunction, they have two arguments. So they are called binary connectives. Okay? What's that? Yeah, it doesn't actually connect anything, but it's just a term. Okay? All right. By the way, this material is coming from that chapter 1 of Handbook of KR, which is linked from the Blackboard. Okay. All right. So are we clear here? Okay. So then let's go to the example. Is this a formula? Yeah, it's a formula. Okay. And one thing that might help you to understand this formula is to parse this formula. So you know how parsing works, right? What is the root node here? Implication. That's called implication. So this is actually the root node. So we'll do root. And the left left tree will represent not P and Q. Okay? So not, okay, oops. Show the answer. Let's do it together. Okay. Okay. So in the left, you see now P and Q. So what will be the root node of that subtree? Conjunction, yeah. And then negation and P. Okay. And same here, Q. Okay. And here it is conjunction, P, disjunction, Q, and negation, R. As you see, the leaf nodes are either atoms, and in this example it's not shown, but it can be also zero-place connective like bottom and top. Okay? The non-leaf nodes can be the logical connectives like conjunction, implication, and negation. Okay? Are we clear? Okay. So then the question is, okay, so let me erase this. Okay. All right. So what is a subformula? So once you have this formula, subformulas are the formulas that are contained in the formula. And in terms of parse tree, you can just relate to the subtrees. Okay? So question, is a formula a subformula of itself?
Yes.
The whole formula? Yes, because it's a subtree, right? Any formula is a subtree of itself, right? So this is, yes. How many subformulas are there? Okay, so let's actually open the Socrates. This is for the first time that we do the in-class quiz. How many subformulas are there? Let me ask you this quiz. So if you open it now, you will probably see the part that you can type the short answer. So I'll give you 1 minute to think. How many subformulas are there? CSE 579. No, I think you should be already in if you logged in before. Okay. Let me close. Yeah, let's see. I should have closed this. I will click out. think I actually opened in two places, so it might got. So in my cell phone, I do see many of you actually choose 11. And somebody says n to the power n squared, which is, where's the n? Okay, let's count this together. Okay, so it's basically counting the subtrees. Okay, how many subtrees are there? We can say P, right, is a subformula. Q is a subformula. R is a subformula. Okay, not P is a subformula. Okay, and not P and Q is a subformula. And not R is a subformula. Okay, Q or not R is a subformula. P and Q or not R is a subformula. And not P and Q implies P and Q or not R is a subformula. I think that's all I have. And there are 9. Okay? Yeah.
So any node you take, the subtree under it is a subformula.
Any subtree, yeah.
For each node, like it's equal to the number of nodes.
Not necessarily. If there's a duplicate, then it doesn't count twice. But for this example, there's none. So, okay. All right. This will be actually useful later when you do the stable model semantics. You will see a lot of subformulas that you have to find. Okay, let's talk about an interpretation. So, what is an interpretation? It is an assignment of truth values to atoms. So when I have signature like PQR, is P true or Q true, R true? We don't know. How many possibilities are there? If you have PQR, and you can assign either true or false to each of them. 8 possibilities, which means that there are actually 8 interpretations. So, okay, I should also say what is a truth value, but false and true are truth values is okay, right? So interpretation is a function that maps signature to truth values. Okay, I just asked you about how many truth assignments is possible. The same question can be rephrased as how many interpretations are there for the signature PQR. So there are 8 interpretations. So interpretation is basically a function, just truth value mapping function. And if this signature is finite, you can actually draw a truth table, which should be familiar. So PQR, so this is one particular function that maps P to false, Q to false, and R to true. You can also write in the more familiar notion in diagram. So P and Q are mapped to false, and R is mapped to true. And we just answered this question. There are 8 interpretations. Now, the atoms are something that is controlled by the truth, the interpretation in the truth table. But once you fix the atom's truth value, then there's no ambiguity in combining those things using the logical connectives. The logical connectives are fixed. Okay? So, there are well-defined mapping. So if you have false and you give it to the negation, it will flip the value. Okay? And if you have conjunction, when both of them are false, the conjunction of false and two false will be the false. Conjunction of two true is actually true. And that's actually the same for the disjunction. But what distinguishes from conjunction and disjunction is when one of them is true and one of them is false. In the conjunction, in that case, it's false. For the disjunction, it is true. Okay, so not surprising because and or has natural meaning there. What is probably not intuitive to you is implication. And this is something that I have to ask you to memorize for now. Okay, sometimes it works as expected, but sometimes it's not. When these for the implication, when x is false, when the first argument is false, it's always true. Okay? And when the second argument is true, it's always true. The only time that the implication can be false is when true implies false. Okay? Just remember that. Okay? And the last one is actually equivalence. When both of them are same values, then it's true. Otherwise, it's false. Okay. Now, evaluation of formula can be recursively defined. So here is actually the formal definition. If you're given an atom, okay, this notation f superscript I means the truth value of f under the interpretation. Okay? Because when you see P as a formula, you cannot say whether this is true or false. But if you're given an interpretation that tells what P, and Q, P, Q, and R means, then you can say P to the superscript I is true or false, basically by looking at the interpretation, the truth table. And this particular symbols, bottom and top, actually has fixed meaning. It's always, bottom is always evaluated to false, top is always evaluating to true, okay? And the negation is going recursively. So if you want to evaluate this formula of the form not f, then evaluate f first under the same interpretation I, and then apply the negation, which means that this can either return true or false, and flip that value when you have negation. And same thing can be said about the binary operators. Okay?
Can you put example?
Yeah, so there will be example in the next slide. Because this recursive definition is actually a bit hard to understand, but this is actually easy to encode in computer. Okay? But one important notation that I want to introduce here is satisfaction. So when the formula evaluates to true under the interpretation, also written as I satisfies F, so this is satisfaction. So interpretation satisfies a formula when the formula is evaluated under the interpretation resulting true. Okay? So same formula can be either true or false, depending on which interpretation that you apply. So let's actually look at example. So this is the formula that you saw before. Okay, so let me ask you. The truth value of this formula, if P is true, Q is true, R is true, then what is this formula? Is it true or false? So recursive definition can be nicely, I mean, for human, for our point of view, picture is much nicer than the definition there, right? So how do you do that? You just fix the leaf node first, okay? So P, Q, R are true. So let's fix this to be true, 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 okay? And then let's evaluate this. If you have studied recursive descent parsing, this is very natural, right? So if we have P here, then negation node will get the value false, because P was true, this is false. False and true is false. Okay, so I have to do this. Can I? Yeah, I can stop here too, right? What is the value here?
True.
True, because when the first argument is false, then the implication is always true. So we are done. Good. Okay. It's actually hard to switch between this. Okay, let's do the next example. What if F is false, Q is true, and R is false? Okay? So, if P is false, then this is true. True and true is true. And now we cannot skip. We have to go to the right subtree. So, false negation is true. True, true. True or true is true. False and true is false. True implies false is false. So, this is false. Okay, so same formula, just different interpretation can make either true or false. Low battery. What about the last one? I'll leave this as an exercise. Okay? All right. The next thing is now we are going to use this notion of satisfaction to build other notions. So tautology. So we say a propositional formula is a tautology if this formula is true no matter what interpretation that you apply. Okay? So for all interpretation, like PQR, there are 8 interpretations, and when you evaluate to each of these interpretations, this formula is always true. Then we say that formula is a tautology. So which one is a tautology? Let's do the quiz here. Uh, Okay, so we started. Let me come back. So which one is a tautology?
Is it a short answer?
It's a short answer. You can say 1, 2, or 1, 2, 3. There are multiple. So. Okay. By the way, this in-class quiz will not be counted to your grade, so don't worry about being right or wrong, okay? But I want you to think. That also helped me how you're following the lecture. So the tautology, so if it is a tautology, then no matter what interpretation that you apply, it should be true. It's actually, we have to exhaust all possibilities here. So one might be better is whether you try to prove this is not a tautology. Can you find an interpretation that is not a tautology? That makes it false, actually. Okay, are you done? Okay, let me close and let's see what was your answer looks like. Okay, so 1, 3, 1, 2, 3, 1, 2, 1, 2, 9. Actually, 9 was not even a part of that. Okay. And, so only 20 answers are there, so I don't know why, but this will also give me who is paying attention. Okay. All right, the correct answer is 1 and 2. Okay, let's see why. In case you're familiar with some transformation in classical logic or propositional logic, this is actually good. So I mentioned to you that in order to understand P implies Q, P implies Q, you can think about this as this way, not P or Q. When P is false or Q is true, then this whole thing is true. So this is actually equivalent. Okay? So with this transformation in mind, the first one is actually saying not P or Q implies not P or Q. Okay? So I don't need to know what is not P or Q, whether it's true or false, but it's always saying either true if implies true or false implies false. It's always true. So this is actually tautology. Okay? The next one, if you apply this transformation, this is not Q or P, and then you have another not P or. Okay? And using some algebra, you can see that this is actually same as not P or not Q or P. Okay? So you don't have to worry about the precedence. And P or not P in the same clause means that this is a tautology. Right? I don't need to care about Q because P or not P together with any disjunction will always be true. So these two are actually tautology. But the last one is not a tautology, so I don't want to even write this. I only need one interpretation that to make this false. What is that interpretation? P is true and Q is false. If P is true and Q is false, okay? Now, I don't want to draw the picture for you. You should do this on your head. Okay, so true implies false is false, right? So this is false, and true implies false is again false. So this is false. So you found one interpretation that does not satisfy this formula, so this formula is not a tautology. Okay, there are two notions that I actually wanted to finish today. but maybe with other materials that I covered, I don't have time to do that, so let me resume from there. Any question up to today's material? If not, then we are going to do exit ticket. In case you were not in the first class, exit ticket will consist of 3 questions. The first 2 will be obvious. The third one is what was teacher's question, but you can understand that question as what are the questions that you have for today's material. Okay? Okay, it's open now.